So again, this is hint pros and cons in the context of monitors, that you have an extra check for each signal thread. Signal thread may in unusual cases wait again. But the signaling thread does not have to restore invariant, and the usual case avoids context switch. It allows broadcast semantics. Okay. I can finally get to Java semantics. The whole idea here is to tell you how to use these things in Java so that you can do your assignments. Okay, and I've built this whole path to it. And in Java, there is no such thing as a condition, explicitly stated at least. Okay, you do a wait, and you do a wait on an object. Okay, and you do a wait in a synchronized method, and the wait is on the current object. Okay, so it's basically this dot wait, this dot notify, and so forth. Which means there's a single condition queue. You don't have a queue for each condition. There is no multiple condition. The condition is implicit. Every object comes with a condition. The object names that condition. And you can do wait, which is our conned wait that I talked about. You can do a notify, which is effectively the conned signal I talked about. Okay? And you have to always put the weights in try blocks. Okay? And in this case, I'm just ignoring the exception. Anybody know why you have a try block around? Sorry? Interrupt exception. Have you guys ever tried to generate an interrupt exception on a thread? Have you ever tried to interrupt a thread? I tried. I couldn't get it to interrupt. So I'm not quite sure when you get that exception. Maybe if the OS interrupts it, that's the thing. But you can in general be interrupted. So yeah, you should do something about it. So my slides become much longer because I have to go for this try block, try catch block. So that's what Gosling did. Single condition queue. Are we restricting ourselves in some sense, in some way, by having only a single condition queue? When Kevin and I looked at this and Java came around, we said, is Gosling nuts? Hasn't he read the Mesa papers? I mean, isn't he educated? How do you do the producer-consumer problem? I mean, that's the classic problem. You have two conditions required there. You have only one condition here. Does it mean we can no longer do the producer-consumer problem? Okay, well, maybe we could actually. We have notify. Okay, so basically what we have is both the producer and consumer waiting on the same condition right now. Producer is waiting on this condition, consumer is also waiting on this condition, and when you do a signal, who are you notifying? Okay, that's just that. I mean, this is what I could do. I could go and make this a notify all. Okay, since we have this broadcast semantics, we just wake up everybody. If the producer is, whoever finds the condition true goes in. It doesn't matter whether we have multiple condition queues or not. Okay, but then the question becomes, do we really need notify all here? And you're saying, I don't. I could just go back to notify and that will work. Will it work for this case, example? We are notifying whoever's waiting on that condition. We are not waiting on that because we notified, that means we must not be waiting. So when the producer goes and does notify, the producer may notify a consumer or a producer. I mean, because they both can wait. So maybe notify all is the safe thing. Or maybe not. Actually, I'm going to argue that this whole thing works with just one notify, without notify. You can never have both the producer and consumer wait. Either the buffer is non-empty or it's non-full. I mean, either it's empty or it's full. You can't have both empty and full. And that's what, Kevin and I said, well, maybe Gosling is just brilliant. We've been doing this producer-consumer problem with two conditions forever. And, I mean, if I ask Jason, right? What's your name? Josh, sorry. If I ask Josh, what would he name this condition? He'll say, what does the name matter? Right? And fortunately, you don't go and name conditions here. If you had to name, what would you say? Either non-full or non-empty? It gets a mouthful. So I don't know if it's the best programming. Yeah.
Well, so you don't like synchronized blocks, but if you use synchronized blocks, I think you can actually have separate conditions.
Okay, let's look into that. I didn't even know about synchronized blocks, so I made a knee-jerk reaction to that last time. And let's look into that. But without what you're calling synchronized blocks, maybe this is fine. Okay. I just find, in the 60s, they used to have overlaid memory. So it was like the variable could either keep this value during the first part of the execution of the program and another value at the end. Just that the compiler could first keep the input file and then use the same space for the output source code because memory was so expensive. And they prided themselves on that. And now, when I always say, hey, what's the name of the variable? That means give me a row. And it better be one row. There better not be two rows. Okay? So it gets confusing. I think modularly it gets confusing. But it does work. Cannot be full and empty at the same time. And bounded buffer is a driving problem. It works. So, Gosling is happy. And that's why I call this mechanism a synchronizer rather than a condition. Because now this thing that you're waiting on can associate with multiple conditions. It's just a mechanism that's being used for all the conditions there are. So the condition and the synchronizer become separated. Okay, in more ways than just having two different things. Okay. So Java was a general hint semantics. So is Gosling brilliant or is he a fool? I don't know. I still haven't figured that out. One of the repercussions is that in its design is that every object has an entry and condition. With the old Mesa design, certain modules were labeled as monitors, some were not. Ones with monitors had an entry queue. And then if you also had conditions within it, depending on how many conditions there were, you could have 0, 1, or as many conditions as well. Now every object comes with these two queues. That means every object is a little bit more expensive, right? Now I've often wondered, why are primitive values not objects in Smalltalk? Why do you have int and integer? Double and capital double. Capital D double. And, sure they're represented differently, but Smalltalk showed a way where you could treat both things as objects. And, when I teach 110 and 401, it's always a pain to tell them, this is what happens with primitive values, this is what happens with objects, and whenever you have to give rules, that means there's something wrong with the language. It's like pronunciation rules in English. It's not phonetic, and people pride themselves on knowing the right pronunciation. I was one of them. Okay? But that's, a kid will pronounce the word right, logically. And then you say, no, that's not the way it is, because in English we say P-U-T put, but B-U-T but. Okay? My grandmother, whenever she wanted to tell us that we shouldn't focus too much on English, that's the example she would give. Okay? So these rules just make things confusing. And this may be one reason. That, you don't want every little int that you have in your program to have a condition queue, entry queue with it. So maybe, we should have just made objects less heavyweight. But that's sort of one thing. But so may need broadcast semantics. Yeah. So even when only one thread is eligible to execute, you might need broadcast semantics because you can't say, you may not have mutually exclusive conditions. So you might just, but that's okay because the usual case is better. And the unusual case, who cares about? Let that be expensive. Okay. So no need for special class labeling as monitor. So it was module and monitor in Mesa. So they had two different keywords. Here you just say public class. It automatically comes with these keys. Okay? And there's no need to declare condition. It's just implicit. You don't have to name it. That's good. One headache over. Okay, you just say this dot wait. Okay, the wait on the condition synchronizing. Okay, let's take another example. Let's say we had a buffer and we had and this is not very realistic. Let's imagine this case that the producer's consumers somehow by magic are scheduled in such a way that whenever a producer goes in, there's always an empty slot, and whenever a consumer goes in, there's always a non-empty slot. Assume that happens. Okay. In that case, I want to make sure that my puts don't interfere with each other, my gets don't interfere with each other, but a put and get can go concurrently. Because, as you see, they are accessing the buffer data structure, but at different positions. One is at next in, the other is next out. Neither of them refers to the other variable. So you can, in fact, it's like if I have a bunch of chairs here, you can be putting your assignment here, you can be putting your assignment there. It's just slots are independent. So assume that somehow by magic, there's some synchronization other than what we enforced through here, where the producer and the consumer just come in such a way. Maybe that's how they arrive on the jobs schedule, that where we don't need put and gets to execute to mutually exclude each other. How might you go and use monitors to define these semantics? I mean, I can go and so puts cannot be executed concurrently, gets cannot be executed concurrently, but puts and gets can be executed concurrently. Okay, so I can always go and put synchronized here, but that makes sure that only one of get or put can execute. Okay, maybe I can go to multiple conditions. I can have a little Boolean variable. If put locked, then wait. If get locked, then wait. And I do a notify all. Okay, because I don't have multiple conditions, so this is what I do. Will this work? So the two methods are checking different conditions. Okay, there's a put lock and there's a get lock. And because I have only one condition queue, I just do a notify all.
In C, it doesn't work because you don't have guarantees about how the values are passed. I was just looking at it yesterday.
In C, they don't have monitors.
Right, but like setting a Boolean isn't, or an integer isn't guaranteed.
Notify and signal, or what is it called? Wait. No, so notify and wait can only be executed in atomic methods. We saw the implementation. I mean, these things are putting things into a queue. A queue cannot be manipulated like in one machine instruction. It's got multiple instructions in there. Plus, we've got this variable put locked, which we are setting to false. That we're testing one place, setting one place. This is not even allowed by Java. You cannot put that. You can only call wait and notify all in synchronized methods or synchronized blocks. So this is not going to work. So what do we do now? Synchronized blocks. I finally got it. This is a very unconvincing reason because I don't even think this is a practical thing. Maybe you guys can come up with blocks. But I can use, okay, so this is not allowed. So what do? And this just blows my mind because, having read Mesa papers and being a reactionary, this seems sacrilegious, but I've just motivated it. Okay? That you're doing the waiting. I mean, you have monitors with no entry procedures. I mean, that's just crazy. Monitors always had entry procedures. Monitors are meant to guard entry procedures and data structures in them. Now you just have monitors. A put lock is a monitor. A get lock is a monitor. You don't have entry procedures. So you don't get this lock when you execute an entry procedure here. You get a lock when you go and say synchronized with that monitor name somewhere else. Not in that monitor, but in some third-party, put class, which is not a monitor. So it's decoupled getting the lock and executing an entry procedure, executing the atomic code into two different things, which, decoupling is normally not very brilliant. Okay, so like I said, this just blows my mind that, how do I even think about this? And I still don't know how to think about it, except, this is the thing. So I go and say synchronized put lock, which means I get this lock. I don't execute code here, but I execute the code in this block. And I say synchronized get lock, okay, and it all works.
Isn't it that you have the get lock and put lock function as the condition, so you could put lock that wait and put lock that notify?
Because put lock is an object that has its own entry and keys to it. I think your entry procedure is like the same entry procedure. It's like when you call synchronize on put, you're synchronizing on this, like the class this. When you call synchronize on
Not
put,
class, object this.
on the put lock.
Sorry?
So when you synchronize on put lock, you're synchronizing on the put lock object.
Yeah.
It has its own one.
Right. That's what it is. So why do I have to do a wait and notify here?
So if you're trying to do wait notify, if you're checking a condition, you could do while the condition put lock dot wait, and then at the end lock dot notify, something like that.
Yeah, but in this problem I don't need to do that.
Right. But I'm just
Yeah, you can do. I'll show you code. You can do notify and put also there. I would love for you guys to come up with nice code that requires this. Okay, I can't come up with a realistic example, so I just invented this example because this code I'm going to show you later also in another context, where it will make more sense. Okay, but so this is your synchronized blocks, and this is again a Java invention. I don't remember having read it in any paper before this. Okay, and you can call it brilliant or you can call it ugh. I don't know, till I find. But it certainly is more flexible. Yeah.
Does it make it more efficient to restrict the area that is actually not? Is that the first?
So when you first said synchronized block, I thought that's what it does. Within a monitor, inside the method, you go and within a method, you say part of this method is locked. Okay. Now here's my purest point of view after that. Somehow that part is different from the other parts. It should be a different method. Okay? That's what I feel. So I'm not a guy who likes inner classes like I told you. I'm not a guy who likes this stuff, but it's very interesting. You guys don't know this, but not much, but the C language was very popular in the 80s. And Kernighan and Ritchie have become very famous. Did they win the Turing Award also by any chance? They might have. They're very smart guys. Okay. And I have hated the language and them all my life. I have just felt I started off as an engineer, and I programmed in Fortran, and that was a joke, I thought. I was a double E major. I was studying, Maxwell's equations and stuff. That was deep stuff. This is just boring I equals I plus 1, which doesn't really make sense to me in Fortran. And then I saw Pascal. I said, wow, and recursion. I said, this is just fantastic, and pre-order, post-order, and heap sort, and wow, that can compete with Maxwell equations. And then what do you do? And then I learned Mesa. And then what do I start to have to program in? C. And if you've seen nicer stuff, you can't stand C. And, these guys who invented these things were OS people. They were practical programmers. The academics in university are not going to invent languages that are popular. So there was just all this C-based languages created, and there were all these bad practices, people with bad practices inventing things for others. So, Gosling also programmed a lot in C, but fortunately, he knew better than to just follow Kernighan, and then who was the guy who invented C++? Struthrup. Okay, so it was so nice to see Java, I'm telling you. I started programming again. I stopped programming between the time I, graduated from college and from university and became a full professor, actually, because that's when Java was invented also. Okay. So we know synchronized blocks, and we see that they serve a purpose. There are things you can do with synchronized blocks that you couldn't do with regular monitors, and maybe this is just really brilliant, because if it's useful, it's brilliant. So synchronized object statement list gets monitor lock at the start of statement list and releases it in the end without entering monitor. You don't enter the monitor, but you get that lock. Okay, so the monitor is now overloaded. It's a monitor, it's a lock, it's a condition queue, it's everything. Okay, which just makes things a little bit. Okay, and what's your lock? I'm just create a good old object, new object. I've always wondered why Gosling allows object to be instantiated. You know, what purpose can a just regular object serve? And I always thought object should have been an abstract class. But here I have a use for it. It's a lock. I mean, it does. Anybody else cringe by saying that a new object is just a lock, Or something, you should have something, but, every object has a queue. Okay? So, that's the stuff. Okay, let's see whether we really understand all this stuff. Huh? So, I am in a monitor. I get the lock, so I'm executing method 1. And now I go and call method 2, which is also synchronized. So I have the lock. Okay, and within the synchronized procedure, I call another synchronized procedure. Do I have to leave the monitor, go in the entry queue and come back, or it's okay? So if I was kicked out, then before from method 1, by the way, method 1 and method 2 are in the same monitor. So before I call method 2 from method 1, I should restore the invariant. But can you make an argument that don't even don't release the lock, just allow it? What bad thing is going to happen if I just allow the method 1 to call method 2 without being kicked out? Yeah, so the producer tried to get. The producer hasn't left method 1. Right? So what you're saying is that when you call method 2, is that what you were saying? That method 2 expects a certain invariant? Yeah, and method 1 okay, so that's a very interesting thing. That it should probably go and restore the invariant to that point. But in one case it's kicked out, the other case is not kicked out. Even if it's kicked out, it has to do that. Yeah. So if you guys, if there was only 3 seats in this and one person left to go to the bathroom and then they have to go and queue up to come back, or they had a seat, right? Let them back in. If they were kicked out, why kick this thread out? You're already in there. Okay? You've got the lock. So it is not that a certain method call has a lock. A certain thread has the lock. That thread can execute so many methods within the monitor, and when it has left the topmost thread that the method will call, it returns. Okay? So you don't have to worry about synchronized methods calling other synchronized methods. That's okay. You keep the lock. This is allowed. Okay? Nothing bad can happen, as long as you restore the invariant before calling method. So once a thread is the monitor lock, it can execute any number of atomic and non-atomic methods before returning from initial method. Okay. Okay, my title is wrong. But now I'm in method 1. I'm in monitor 1. I want to next call method 2 in monitor 2, which means I have to get the lock of monitor 2. When I go to call method 2, before I call method 2, should I release my lock? It's like, when I was teaching for the other class, I was teaching that class in a room downstairs, and I went in, because the room was small, I got another room elsewhere too. I kept the other room too. I said, after people drop, I want to come back to this original room. So I keep both, or do I say, hey, I'm reserving that now. Let somebody else come here. So which would you like? Which semantics would you like? Forget what Java does. We don't know what Java does. Even, what makes sense?
I feel like if you release the lock, what does that mean? In that country, you can get into deadlock if you have to release. If no one wants to lock in.
You can definitely get into deadlock if you don't do that. Okay, so that's the disadvantage. And your scheme requires me to go and maintain my, to go and restore my invariant before calling method 2. Okay, which may not seem such a bad idea, because I have to do that in method, then I call method 2 here also. But then I can't execute both methods atomically.
Are you also assuming that when you enter method 2, the invariant for method 1 holds?
No, I don't have to. If I don't leave method 1, I don't have to assume anything about monitor 1.
Yeah, that's right. But the issue then is also still when you come back to method 2.
When I come back from method 2, so one approach is to not release my lock. The other is Will's approach, where I release lock. Okay, if I release lock, then of course I have to restore my invariant, go back into the queue. Now, you might want to go and execute, so you have pros and cons, right? So you might want to execute method 1 and method 2 atomically, or you might want to go and not get into deadlock situation. Now in Java, if you want to execute method 1 and method 2 atomically, do we have another way to do it? A synchronized block. So you would think that it should release. It already has a way to do those things automatically. Okay, but I don't believe it does. You keep your lock. When synchronized method in one monitor calls synchronized method in another monitor, it does not release lock of the first monitor. And so, we talked about this. It can execute both atomically, doesn't restore invariant, but can lead to deadlocks. And that's what you see here. That here's one thread executing method 1, here's another thread executing method 2, one there, and Europeans call this deadly embrace. Okay, they're more colorful about it. So they're just, neither one is going to leave the other. So Java doesn't do it. Java has the synchronized blocks, it could. Okay? But from what I remember having when I used Java, it doesn't do it. It may have changed things right now. Okay, let's see if we further understand things or not. So when method 1 in the middle calls wait, does it release the lock? I'm waiting on myself. So here's a thread. It's calling method 1 and it does this dot wait. Do we release the lock? We saw it does, right? So you call this and the lock is gone. Okay, we seem to understand that. So lock release when wait called on this in a synchronized method. Okay, now that we have this funny synchronized blocks, when method 1 goes and says putlock.wait, where putlock is another monitor. Now we have this crazy world where monitor code in one monitor can call wait in another one. What do you think happens at this point? So I am in some object which has a reference to another monitor, putlock, and within there I go and say, within a synchronized method I say putlock.wait.
That lock, the putlock lock is really other things that are synchronized on putlock can get in.
No, I'm waiting on putlock. I'm not calling some method. I'm not saying synchronize. I'm just saying putlock.wait.
Yeah, but like there are probably two threads trying to access something that's synchronized on putlock.
They could be.
And so when you call wait on this one,
should I go and so I'm in monitor 1. That's one object. There's another monitor that's called putlock. When monitor 1 goes and says putlock.wait, clearly I have to go and wait on monitor 2 putlock's thing. Do I release my monitor 1's lock? Or is this even allowed? And if it's allowed, what is semantics? I mean, we get into all these issues.
Are you just saying having a synchronized method that can contain the synchronized form?
There's no synchronized blocking.
Okay.
Synchronized method, called method 1, has a reference to an object called putlock.
Can you call putlock.wait if you're not synchronizing putlock?
Yes, I did it. I wrote this code last night. You can write this code. You can even execute it. It won't do anything. Okay. So you have your lock. You execute this. It does nothing. Okay. So I said if I do a wait, in the debugger I should wait, right? I should just block there. The debugger just goes merrily right through it. Says putlock.wait. Okay. Wait. Go next. Then I tried putlock.notify. It says, oh, illegal monitor state exception. So I can't do putlock.notify, but I can say putlock.notice, wait. And we don't have to worry about whether it releases lock or not because this operation does nothing. Okay? This kind of shows Java's been hacked a little bit. Okay. I can do this though. Okay, this is what you were talking about. I can say synchronize on putlock, and I can do putlock.wait there. In general, synchronize statement does something. You can only wait on a monitor associated with the block. In Java, synchronized statement block and wait on. I think here's the note. You can wait or notify condition queue of monitor only if you have the monitor lock.
If you have a synchronized method, or a synchronized block inside a synchronized method.
I assume you should be allowed to have it, but I don't know what that. You're just trying to get 2 locks at that time.
And then if you wait on the putlock inside if you wait on the putlock inside the synchronized block, does it release the lock of the outside synchronized method?
And what do you think?
I'd probably say yes.
But it doesn't do it when I call from one monitor to another monitor. So it's I would think. So I have never read a manual on Java. Never. I knew Mesa, I knew Smalltalk, I just figured out and I knew Gosling was smart. And I did these 3 things together and I assumed my semantics. And I'll just tell you how I got badly burnt based on that. Okay, now let's try this. Method 1 is executing. It calls thread.sleep for some time interval t. Release lock, not release lock. Not release. Why? So you're saying that it may have gone beyond the sleep thing? When you say sleep for 40 milliseconds, what are you guaranteeing? You are eligible to execute after 40 milliseconds. When you actually execute, depends on who is executing at that point. I mean, just imagine, I book this room, Diane wants to come and teach, and I go and tell, I book a room in a hotel. Everybody wants that room. I go and tell the hotel clerk, I'm going to sleep, give me an alarm at that time. Well, room I need to, not a good analogy, okay? But the system knows you're going to sleep, you're doing nothing. Keep the entry procedure? I couldn't imagine anybody smart doing that. But that's what Java does. I wrote this complicated piece of code, and there were so many things where it could go wrong, and it did go wrong. I checked all of those things till I finally traced it to this semantics, that you actually keep the lock. And I just can't believe the amount of it there, because I can't think of an application where you need that. Okay? So I spent a good 1 day of my life. Not because I didn't read the manual, right? So any blocking operation, I believe. Now I don't know other blocking operations, but you should be uniform. Any blocking operation will keep the lock. Basically, in Java, you're not releasing the lock, except if you're doing a wait on this. You don't release the lock. Okay. And I think I was stumped twice by either the same thing, sleep, or two different system calls. Even though waiting method can do nothing, and Java knows it is waiting. It's not as if Java doesn't know it's waiting. You went through Java to tell you that you're going to sleep, but you keep them on. Okay, and I did this because I was delaying messages and so forth, so I was doing sleep.
in different queues in one of the monitor queues?
Yeah, that's the whole point. See, I'm an OS guy. I know it goes into a sleep queue, and you keep a thread only in one queue at a time. You don't keep it in two queues. It's just mind-boggling that this is what I get for knowing how to implement things. Exactly. It goes into a sleep queue, a sleep delta list. So, but that's what, and this is what it seems to be. That if you go into any queue, if you go into an I/O queue, you go into the queue of another monitor, you keep the lock. Okay? These are things you need to know. Okay, hopefully we can finish this stuff today, but maybe we won't. Now, here's, we introduced monitors as a way of doing a higher level solution than semaphores. But when it came to doing signals and notifying, we're down to the semaphore level. In fact, in some sense, we're even lower level. We don't even have a count associated. We keep our own count. So, we have declarative for mutual exclusion, and we have procedural for other synchronization. Could we do maybe other synchronization also declaratively?
So you could do certain object types check for certain conditions. So if you have, so there's interfaces that you could say that are sending certain data types. And certain, I'm just trying to give a class that check for certain condition types and you could use that to declare as well.
So you have some predefined semantics, you're saying, built in procedurally, and you just use them somehow. Yeah, no, I don't want to ever write code myself doing procedural stuff. I don't have to do one wait and notify, and if I do a wait and not a notify, I get into the same problems that semaphores have for mutual exclusion. And how could we do declarative synchronization? I won't be able to finish this today, but let's just start it. And the hint is, I can have a finite state automata, or I can have a regular expression. Finite state automata is procedural. Regular expression is declarative. So we want somehow regular expressions. We're going to write a regular expression like things. Now, regular expressions are restrictive. You can't do all Turing complete, all computations using regular expressions, but certain you can do. We also do certain only. If we could, because of the halting problem, we can't go and do arbitrary computations and declaratively. Okay? We do the producer-consumer, we're happy. Okay? In a general way. And before we do that, let's go and take this class. We're going to remove all of the synchronization code in it. Okay, this is our goal. No synchronized things. Mutual exclusion is also specified declaratively using this some language we'll have, which will be like regular expressions. We're not going to have any weights and signals. Okay? Which means we don't have any code that invokes that either. And if we are not going to have mutual exclusion, if we are not going to have synchronization when we get input, we don't need a size variable. The size variable is just meant to synchronize those two. Okay? It's not needed if there is no synchronization need. Okay? Which means we don't even declare the size variable. So we're going to look at something called path expressions, okay, which are going to be like regular expressions. Now, regular expression is what? If I was to ask you to define regular expression, what would you define? Are you doing five? Whatever this five? Have you done this class? The regular expression class? What's it called? 5 of computation. So what's a regular expression? If I was to say, yeah. Okay, so you take a vocabulary, which is normally characters, it could be anything, and you have operations on the vocabulary. So if the vocabulary is normally characters and regular expression, In part expression, what will the vocabulary be? So what are you saying? You're saying, I'm giving you constraints on the sentences you built with the alphabet. In synchronization, I'm going to be giving you constraints on what? No, but condition variables are constraining what? In one case, it's saying what are the legal sentences. In this case, it's going to say what are the legal, not, and legal means what, well, let's just, what are legal what? What is going to happen? Very good. And things happen in what? Okay. So there's some vocabulary, and this vocabulary is the set of methods in some module. I'm going to say, I'm going to give you legal sequences of invocations of these methods. Okay. So okay, these are method calls. Okay. So one operation is alternation. By the way, do you guys say it's A vertical bar or A plus B? Vertical bar? Yeah, it's been a long time. Anybody? Even when I studied, we used to say A plus B. So I look up the Wikipedia syntax and they say A vertical bar. So this means the next character I'm matching. Okay, so you're matching. In regular expression, you write essentially a finite state automata, and it's got to figure out, what is the next thing it should match. The next thing I'm matching could be an A or a B. What's the equivalent you can write in the case of path expression? The next method you can call could be either get or put. It should be M1 or M2. Okay. That's an example. So in general, regular expression, any member of the alphabet is a regular expression. Any call, any method between M1 and Mn, a call to it can be a path expression. Okay. You can say R1 equals R1 R2, and what does that say? The next expression I should match, the next thing I match should first match, okay, then R2. You say P equals P1 semicolon P2. First match the path P1, then match the path P2. Okay. I guess we are out of time, so we'll just let's just R1 or R2. Well, we'll just start off from here next time. So first P1. Oh, sorry. Yeah, I'll correct that. So we were looking at synchronization, okay, and the problem we saw, or the last problem we want to look at, is how to make all synchronization declarative. Okay, so far we said, okay, mutual exclusion. There's a very nice way to do declarative there. You just declare your methods to be synchronized, and you're done. Yeah, and there's all kind of issues with the method calling from one monitor to another monitor and so forth. But at least if you don't do anything tricky, that works just fine. Okay, if you do something tricky, then you might have to just resort to your own kind of synchronization, where you don't rely on synchronized methods. Okay, but if you had semaphores, you could use a lower level synchronization mechanism. And then we said, why not try to do everything declaratively? Because then the code is not messy, and it's just higher level. Okay? So we said, okay, the intuition is just as when you're trying to scan tokens, you can use either a regular expression to describe what each token should look like, or you can write a finite state automata or some program. Okay, and that program will basically have the power of a finite state automata. Okay, it's not something that needs a more powerful language. So similarly, what we can do is, other than writing code that does signal and wait on conditions or on semaphores, we'll write these path expressions. Okay, so regular expressions, we saw the vocabulary was some set of elements, and those elements are typically characters. And now our vocabulary will be methods. Okay, and we're putting constraints on. In the case of regular expression, we are putting constraints on what characters can form a legal sentence, or the other way around. The structure of a legal sentence. In here we'll go and put constraints on what legal method calls are. Okay, relatives to some module, some class. Okay. So these are usually characters, could be anything, these are method calls. So it defines legal sequences of vocabulary elements, defines legal sequences of method calls in a module. So you say, for example, I can accept A or D. So I can go and invoke next either the get method or the put method. Okay, so very similar. Syntax is a little different. And let's be a little bit more rigorous then. So what's a regular expression? Any letter in the alphabet is a regular expression. Okay? Any method defined in a module is a path expression. Okay? You can say this method should be called. You can concatenate regular expressions. You can concatenate method calls. Okay? So you're saying R1 must be followed by R2. P1 must be called after P2. I guess I didn't correct this. So P2 must be called after P1. R1 or R2. So R1 or R2 is legal. Call to P1 or P2 can be made. And then we have the Kleene star, okay, which says that how many instances of R are acceptable? 0 or more. 0 to infinity. Okay. So equivalent here is that any number, so 0 more occurrences of R can be matched next, 0 more occurrences of call to P can be executed. Okay, so you can execute P, followed by P, followed by P, followed by P, any number. You can make 2 Ps, 1 P. Okay, so it's very analogous. Plus, you can have this. Anybody want to guess what this means? I shouldn't say call to P. This is a regular expression. So occurrences of P, okay, which can involve multiple. Okay. Up to n concurrent executions of P can be. Okay. So you know that in regular expressions you can't count. Right? So here we are saying you can count. This is more than regular expression. Okay. So let's go and see whether this new bag of tricks we have, how can we apply that to the mutual to produce a consumer problem, and we'll assume that we have just the put and get methods. Okay, and remember we removed all synchronization code. So we are saying there's no size field. Okay, and put goes and puts something at the next in position, and gets the value from the next out position. So if I want to specify just mutual exclusion, forget about worrying about empty buffers and full buffers. What path expression do I need? So what should I say? Get or put, and there can be infinite sequences of this. So this could be, these are all equivalent. Okay, if you don't put a square bracket around this, it means an infinite sequence. Okay. So does that really do it? So the next method can be get or put, and you can have up to infinite executions of this sequence active at any one time. So what are, by the way, the mutual exclusion elements? What are the mutual exclusion constraints? Just say that in English. No, this is mutual exclusion. Forget bounded buffer. Assume this is unbounded buffer and somehow all is filled. So you can't execute a get and a get at the same time because? What about put and a put? What about a get and a put? That's fine, actually. Okay, one's going at next in, one's going at next out. Sure, they're accessing the same buffer, but they're accessing different parts of the buffer. Then we have a more fundamental problem, that the buffer is empty. Okay. So how do I say that in regular expression, what you just said? So what do we want to say again? How many sequences of gets can you have at any one time? How many of put? What's the order of the get and put? So how would I say it? Semicolon means sequence. Commas or. But and is semicolon, but do we want to go and put an order between get and put? We're just doing mutual exclusion at this point.
So, well, like, it doesn't matter if you get comma, put, or semicolon, put, comma, get.
So an arbitrary number of activations of get or put can, by the way, what this is saying is an arbitrary number of activations of get or put can be executed concurrently. Okay, so square brackets, implicit and outermost operation. So that's what we are saying. An arbitrary sequence, so we don't want that. Right? So if I go and put this, what do I say? Okay, so that's what you first wanted. That's too strict, right? I can't execute a get and a put at the same time. I don't know why they just didn't use bracket. Bracket means star, cleaning star. Parentheses is preceded by a number.
Is it a typo in there? Is it parentheses on the left and a bracket on the right?
Yeah, that's a typo. Sorry.
Oh.
Yeah, I don't know why they could have just put a number before that. So what do I say now? To get it to make it more flexible? But that'll still no, but we don't want that. We want a 1 there. So 1 is going around both get and put. What you want is a 1 around only. Okay, so put and get can be executed concurrently as no shared variable. So we want one of get, one of put, doesn't matter what order they're executed. Okay. Yeah, so that's a comma.
So I'm just thinking in regular expression, you couldn't have both happening at the same time.
Yeah, regular expression was just an analogy.
Right, but I'm just...
They're saying that, at the next point, so you can have one sequence of get, one sequence of put, at most one sequence of get, at most one sequence of put, and that means concurrent. Comma means concurrent.
Okay.
Exactly. Okay? So that's your mutual exclusion. And it's more flexible than what you could do with monitors. We haven't done the empty buffer business. That's why it's so cool. But we'll do that empty and full buffer thing next. Okay? So only one execution of get or put can be active at any one time. So let's now forget about mutual exclusion. Let's worry about synchronization. So we don't want the consumer to go and call a get if there's no. So we don't have any conditions, there's no size variable, so what in path expressions gives us the power to go and specify something like that? Semicolon, because? Okay, so you want to say, must define an order between get and put. Basically you want to say that gets must follow puts. Okay, each get must be preceded by a put, and they can be, and this, what is this saying exactly? Each get must be preceded by a put, and how many activations of these sequences can be around at any one time? Infinite, right? So this is all equivalent. Okay, so an infinite number of concurrent put get sequences possible. So that's not what a bounded buffer is. It's an unbounded buffer. So how do I do a bounded buffer? Now you know why that n was put. It was put in just for the bounded buffer problem. So if I go and put 1, that is a bounded buffer of what size? Okay, or a single put get. The two methods alternate, a bounded buffer of size 1. I've got now a bounded buffer of size n. Okay. Questions? So up to n. Remember, n is not required. It's up to n activations. It's not like a n, b n in a context.
Just use non-atomic operations on shared variables. So you can increment next in before assigning values.
So each method is executed atomically.
Okay. Well then,
No. Wait a minute. So what's the problem you're saying?
So we're assuming that put and get are not atomic because they're going to occur concurrently in effect.
As right now. Okay. So right now we don't have atomicity.
Right. So
we have
still in this case, because you're assigning a value to next in and incrementing it in the same step, you can increment it before assigning it because that operation is an atomic.
Yeah. So we don't have atomicity right now. Okay. So puts can execute concurrently with put. Okay, that's what you're saying, right? So I have a mutual exclusion by this. I have synchronization with this. How do I put them together? I want both now.
Inside the end.
Okay. This is somewhat confusing. The one is not sort of, one is a global value you're putting. You're saying you can have at most one active globally. Okay. It's not as if you're saying it's within the N1. Okay. So it's N activation of put get can be active and only one activation of put and one activation of get. So N path expression gives global restriction, not within sub expression. Okay. It's not that this is a value within the sub expression. It's not that each N can have one. For all N's put together, there can be only one put executing at one time. Okay. Neat? Even if nobody implements this, you at least understand things a little better, right? Okay, so let's see if we can do other problems. You guys know what the reader-writer problem is? So reader-writer problem is that there's some threads that read a value, some threads that write a value. Okay. And what kind of constraints do you want on concurrent executions of these threads? You can have concurrent reads as long as, if one person is writing, can you be reading? So you can have, as long as, if you have one writer at all, so the writer enters, nobody else can enter. But without a writer, as many readers as you want can. So how might you specify that using a path expression? So there can be an arbitrary number of readers or a single writer active at any one time. And this just... suppose you could put, what if you put one inside? Then, if you put one inside, here, can you? Because we said that the one applies globally. This is more intuitive to me, because it's saying you can have one instance of all of these together, but the fact that the one applies globally is not very intuitive to me. But I think that will still go according to semantics, that one writer or infinite number of readers. Okay. Now, there's also a fair readers writers, that the readers should not starve out a writer, because as long as there's a reader and this, and if there's a reader and a writer queued and the reader's right now inside, the reader can always go in without the writer ever getting it. And how would you do that using path expressions? Well, you can't. Okay. That becomes too heavy. So how many of you have done fair readers writers in operating system classes? The semaphores. It's a mess. Okay. But it can be done. And here we go and see that because it's messy and complicated, it's not cleanly done. So just as regular expressions cannot handle all languages, path expressions cannot handle all synchronization schemes. Okay. So method calls are matched according to specified path expressions, and method calls that do not match are blocked. So you sort of wait for that to happen. And after the top level method expression is matched, it can be matched again. So one get put, when once it's matched, you can sort of match it again. The implementation is unspecified. How you do this, it's up to the implementers, and I don't think this ever got implemented. But it's certainly a good way to understand synchronization, just to try to really understand what's going on, and you don't get bogged down in the code. And then you can implement code. And maybe, just people who invented this were lazy, they didn't know how to implement, and if they never sort of were good salesmen for their idea, then maybe this is quite powerful. But it's very, very few people know about this concept. I discovered this in a paper, and I've always sort of got turned on by the concept, and it just seemed like a natural progression for monitors. So I put it in class also. Okay. Questions?